Welcome back. In this video, we'll go through some examples to get comfortable with calculating equivalent resistance. If you haven't already, watching the previous two videos is recommended as they provide the foundation for today's lesson. You can find the link above. We will start with a basic example to cover the fundamentals, and later we'll tackle more challenging ones. So, stay with me until the end. All right, let's dive into this first example. What we're aiming to find here is the current flowing through the battery. To figure out the current through the battery, we'll need the resistance between nodes A and B. Once we have that, we can use Ohm's law to calculate the current. So let's begin by finding the equivalent resistance across nodes A and B. Let's start with the two resistors in parallel. To find the equivalent resistance of two parallel resistors, we multiply their values and then divide by the sum. This method works only when we have exactly two resistors in parallel. Using this approach, we get the resistance between nodes B and C as 2.4 ohms. After replacing the two parallel resistors with a single resistor, we're left with two resistors in series. To find the equivalent resistance for series resistors, we just add their values. This gives us an overall equivalent resistance of 10 ohms. Now, applying Ohm's law, we calculate the current flowing through the battery as 0.6 amperes. I know it wasn't much of a challenge to find the current flowing through the battery once we determined the equivalent resistance. Nevertheless, I hope the explanation was clear. Let's move on to the next example. Just like the previous one, we'll need to find the equivalent resistance between nodes A and B. When given a circuit diagram, the first step is to check for any resistors in parallel or series and replace them with their equivalent resistances. After that, look for symmetry and equipotential nodes. In this circuit, we don't see any symmetry, but later in this video, we'll explore examples that do. In this diagram, we can spot two resistors in series, so let's start by calculating the equivalent resistance for these two. The equivalent resistance of two resistors in series is simply the sum of their values, so for these two resistors in series, the equivalent resistance is 20 ohms. By replacing the two 10-ohm resistors in series with a single 20-ohm resistor, we now have two 20-ohm resistors in parallel. To find the equivalent resistance of two parallel resistors, we multiply their values and divide by their sum. However, since these two resistors are equal, we can also find the equivalent resistance by taking the value of one resistor and dividing by the number of resistors in parallel. Either way, we end up with an equivalent resistance of 10 ohms. When we replace the parallel resistors with their equivalent resistor, we're left with a circuit where the two resistors are now in series. To find the equivalent resistance of resistors connected in series, we simply add their values, just like we did earlier. Here, we have two 10-ohm resistors in series, so the equivalent resistance of these two is 20 ohms. All right, we're down to the final step, finding the equivalent resistance of these two parallel resistors. To do that, we multiply their values and divide by the sum of the resistances. This gives us an equivalent resistance of 10 ohms, which is the total resistance between nodes A and B. Since the two parallel resistors have equal values, we could simply divide the resistance of 1 by 2 to get the same result. This is a useful shortcut when dealing with identical resistors in parallel. Just take the value of one resistor and divide it by the number of resistors in parallel. All right, let's dive into another example that's a bit more challenging than the previous two. As in the earlier examples, our goal is to find the equivalent resistance between nodes A and B. At first glance, it might not be obvious, but resistor R2 is in parallel with resistor R4, and similarly, resistor R3 is in parallel with R5. Let me redraw the circuit to make things much clearer. We can now find the equivalent resistance of these two pairs of parallel resistors. Let's use the shortcut to find the equivalent resistance of the two parallel resistors. This is the circuit diagram we have after replacing the two sets of parallel resistors with their equivalent resistors. Now these two resistors are in series. To find the equivalent resistance of resistors in series, we simply add their values. We are down to the final step in determining the equivalent resistance between nodes A and B. To do this, we calculate the equivalent resistance of the three parallel resistors using the formula for resistors in parallel. After applying the formula, the equivalent resistance of these three parallel resistors comes out to 2.67 ohms. That wasn't too difficult once we figured out which resistors were in parallel and which were in series. Let's move on to another example with a similar type of challenge. At first glance, it might not be immediately clear how the three resistors are arranged. To make it easier, we can identify each end of the resistors based on how they're connected. One end of this resistor is connected to node A, so we'll label it as A. Similarly, the other end is connected to node B, so we'll label it as B. This approach makes it easier to understand the connections within the circuit. One end of each resistor is connected to node A, while the other end is connected to node B. To better visualize the resistor configuration, we'll arrange each resistor between nodes A and B and redraw the circuit diagram. Now it's clear that the three resistors are in parallel. Since all the resistors have the same value, finding the equivalent resistance between nodes A and B becomes straightforward. We can simply divide the value of one resistor by the number of resistors in parallel. In this case, with three resistors in parallel, we divide the value of one resistor by 3 to get the equivalent resistance. I hope everything we have covered so far has been clear. In the first two examples, identifying the parallel and series resistor combinations was fairly straightforward, which made calculating the equivalent resistance between the given nodes easy. However, the next two examples were a bit more challenging, as spotting the series and parallel resistors wasn't immediately obvious. By rearranging the circuits, we managed to identify these combinations. From here on, we'll dive into examples that require a deeper understanding of symmetry to determine the equivalent resistance. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. Let's start with this example. Our goal is to determine the equivalent resistance between nodes A and B. First and foremost, start by checking if there are any series or parallel resistors in the circuit that can be replaced with their equivalent resistances. In this particular circuit diagram, no such combinations are present. Next, examine whether the circuit exhibits symmetry, either along the direction of current flow or in any other direction. In this case, the diagram displays symmetry in two directions, along the current flow, AB direction, and in the CD direction, which is referred to as mirror symmetry. You can choose either type of symmetry to simplify the circuit based on your preference. For this example, we'll use mirror symmetry to simplify the circuit. In the next example, we'll apply symmetry along the direction of current flow. In a symmetric circuit like this, no current flows through the resistors along the line of symmetry because the voltage at nodes C, O, and D is identical. This allows the circuit to be simplified in two ways. either by removing the resistors along the line of symmetry, leaving nodes C, O, and D unconnected, or by joining these nodes together, since they share the same voltage. Both methods achieve the same result without altering the equivalent resistance, and the choice of approach depends on which option leads to fewer steps for calculating the equivalent resistance. Feel free to check out the 2 videos I made before this one, where I've explained this concept in much more detail. The links are provided below. Now, we can simplify this circuit by combining the 3 sets of series resistors and replacing them with their equivalent resistors. This results in 3 parallel resistors of equal value. To find the equivalent resistance of 3 equal parallel resistors, we simply take the value of one resistor and divide it by the number of resistors in parallel. In the end, we determine that the equivalent resistance between nodes A and B is 2 ohms. Let's move on to the next example. This circuit diagram is quite similar to the previous one, with the only difference being the values of resistors R3, R5, and R8. While this change eliminates the mirror symmetry, the circuit still retains symmetry along the direction of current flow from A to B. Now, the question arises, can we remove resistors R2 and R7? The answer is yes. Since the voltage at nodes C, O, and D remains identical, no current flows through these resistors. This allows us to remove them without altering the circuit's behavior or its equivalent resistance. The principle behind this was explained in detail in my previous videos. I kindly encourage you to check those videos to understand the rationale behind equipotential nodes. The links are provided below. From this point onward, we can follow the same steps as in the previous example. First, calculate the equivalent resistance of the series resistors, and then find the equivalent resistance of the parallel resistors. By simplifying the circuit step by step, we ultimately reduce it to a single equivalent resistor with a value of 3 ohms. I hope these 2 examples provided some insights into how symmetry can be utilized in a circuit diagram to determine the equivalent resistance. We'll explore another example where symmetry is used to find the equivalent resistance. In this circuit diagram, all the resistors have the same value. Our task is to determine the equivalent resistance between nodes A and B. This circuit clearly exhibits mirror symmetry, as it is symmetric along the line connecting points C and D. The line of symmetry passes through resistors R1 and R8. Unlike previous cases, we cannot remove these 2 resistors because the symmetry line does not align with their direction. However, since all nodes along the symmetry line have the same potential, we need to introduce a node on this line. To do this, we replace the resistor intersected by the symmetry line with 2 resistors in series, ensuring their combined resistance equals the original resistor's value. This adjustment preserves the circuit's symmetry and simplifies the analysis. Since all the nodes along the symmetry line share the same potential, the groups of resistors on either side of the line are effectively in parallel. This allows us to simplify the circuit further by replacing each group with a single equivalent resistor. Let's rearrange the resistors in the circuit to make the series and parallel connections more apparent. In this circuit, we have 2 sets of resistors connected in series. For each set, the equivalent resistance is calculated by summing the values of the resistors in series. At this stage, we have 2 sets of resistors connected in parallel. To calculate their equivalent resistances, we use the formula for combining parallel resistors. Once replaced with their equivalent resistors, the circuit simplifies to 2 resistors in series. Adding the values of these 2 series resistors gives us the final equivalent resistance between nodes A and B, which is 32 ohms. I hope you now have a solid grasp of how to identify symmetry in a circuit and the systematic steps required to simplify such circuits effectively. In the next section, we'll delve into a fascinating type of resistor arrangement called ladder circuits, which have an infinite extension. A ladder circuit is a repetitive network of resistors, with each rung adding a fixed configuration of resistors in series or parallel. The first step in analyzing these circuits is to recognize this repeating pattern. Due to the infinite extension of the ladder, adding or removing one segment does not affect the circuit's overall equivalent resistance. This unique property is fundamental to solving problems involving infinitely long ladder circuits and simplifies the process of determining the equivalent resistance for such configurations. Here, we have an infinitely long ladder circuit consisting of 1 ohm resistors. To analyze this circuit, let's remove the first rung of the ladder and concentrate on the remaining portion of the ladder. Since the ladder is infinite, the equivalent resistance of the remaining rungs remains the same as the original ladder. This self-similarity property is key to solving the circuit. We can replace the infinitely long section of the ladder with its equivalent resistance, as this substitution preserves the overall configuration of the circuit. This simplification takes advantage of the ladder's self-similar nature, enabling us to systematically determine the equivalent resistance. To find an expression for the equivalent resistance, we begin by simplifying the circuit. First, we replace the two resistors in parallel with their equivalent resistance. Then, we combine this result with the other resistors in series to determine the total resistance. This total resistance represents the equivalent resistance of the entire ladder, which remains unchanged due to the self-similar nature of the infinite ladder circuit. By simplifying the equation step by step, we can derive the final expression for the equivalent resistance of the circuit. After solving the equation, we obtain two possible values for the equivalent resistance. However, since resistance cannot be negative, we discard the negative value, leaving us with the positive result as the equivalent resistance of the ladder circuit. Thank you for watching this video all the way through. I hope it helped you better understand how to determine the equivalent resistance for various types of circuit arrangements. If you found this video helpful, please give it a like, share it with your friends, and don't forget to subscribe to the channel if you haven't already. Your comments are invaluable. They not only encourage me to create more content, but also help me improve future videos. Until we meet again in another video, take care and goodbye.